Okay, so let's get started. So today we will talk about RLVR, which is a continuation of the uh, previous two lectures on RLHF. This will be the last lecture of large language models. As we mentioned, so we drag a little bit longer for the reinforced learning, which definitely is a pretty important topic in the current large language model developments. So RVR is concept started, I think, maybe a year ago, around maybe a little bit more than a year, 1.5 years ago. And particularly, I think in OpenAI, there was this Strawberry project resulting in O-series models, the first reasoning models, which demonstrate the power. And then later on, other people follow up. Particularly, we will talk about along this in the open source domain will be mainly developed by DeepSeek. Certainly, there are other developments also in the Frontier Lab. There were closed source developments, but the one we talk about, which pretty right now pretty accepted in the open source, will be along this DeepSeek. But essentially try to train reasoning model, doing mathematics and reasoning and so on. So that's around a year ago, and that becomes pretty important topic, and it gives model more capability. Compared with RHF, if you think about the difference, we will talk difference more, but the purpose is somewhat different. For the RHF, usually the purpose is for alignment. Basically, let the AI or LLM can answer questions in a flavor that human favors, basically according to human preference, right? It's a little bit more related to safety, related to helpfulness, and how human feel comfortable. And the direct application is chatbots, which you work with. RLVR, the purpose isn't that. In fact, if you look at what actually going on, there could be slightly conflicts or slightly different direction, I would say, not say conflicts, but basically they are really trying to gaining capability of LLM in the sense of thinking, in the sense of reasoning. So essentially, they generate tokens to in the process in order to achieve a certain outcome. So so nowadays all the reasoning models using are trained using this kind of approach. There are variations of approach. The closed source may not using exactly the same algorithm we are talking about, but this algorithm definitely effective. And also they are widely known in the open source and academic literature. So we will focus on the talk. Yeah, we'll talk a little bit about the, I think that's a high-level overview, but we will talk more details about exactly what is RH and RVR to give you better idea about the differentiation. After that, we will talk a little bit about policy gradient-based learning. This is just for the purpose of introducing the GRPO. So those are at a high level. If you look at the exam sample questions, they are also at high level. So we do not give sufficient details in the sense of to be very deep, but at least you understand what is happening. And eventually we'll talk about the GRPO, which becomes a standard algorithm used for RLVR. This is published actually earlier than their later more influential paper, DeepSeek Math. The algorithm already there. They are looking at mathematics, using LLM to do mathematics, which is very much related to the reasoning. Because when you do math, you need to do reasoning. Turns out this reasoning can be generalized to other tasks. So it can be a general reasoning model. DeepSeek R1 is the one which really demonstrated that this recipe and can actually train very powerful reasoning model. At that time, the open source model is certainly reasoning is basically this is the best reasoning and also comparative to some closed source models. Later on, of course, a lot of other companies adapt the same type of techniques or similar techniques, at least using RVR, and then they also catch up. So, but I think before that, around the DeepSeek R1, it's probably the beginning of last year. It's January last year, roughly. That was regarded as really kind of breakthrough in terms of open source, and in terms of training reasoning. So essentially, they can, of course, OpenAI, they have a slightly different strategy. They already trained the models like O1, right? A few, maybe a half years earlier, or other models like they are all going. And currently, I mean, these are also important. People starting to shift again. So if you think about 2 years ago, right, people talk a lot about RLHF. The field developed very fast. 1 year ago, it's talking a lot about reasoning. Now it's talking about agents, right? So the agentic models are also quite related to reasoning. You have to be able to do reasoning in order to do agents. So therefore, this is still part of the solution. So, but you probably need more. So the field evolves very fast. But reasoning is very important. It is certainly it's a the difference of RHF or reasoning is you really give LLM more power, right? So essentially, something you cannot do in pre-training, by training this RL, you will be able to do. We will see, look into this DeepSeek R1 paper, there's some high-level conclusions, then we will see that. Okay, so basically, yeah, again, so for the open source, they are mainly pioneered by DeepSeek, and then we will talk about their papers. So this time. So let's talk about from RHF to RVR. We already give a high-level view about that. Essentially, RHF, that's in the open source community is 2 years ago, as I mentioned. So it's about focus on alignment, health needs, safeties. Technically, we know that you need to learn a reward model from human preferences. Although there are algorithms like DPO, they just learn directly from human preferences without reward. We also mentioned that you can improve upon that with a reward model. So basically, typically, the standard pipeline, at least the first reward model, and then learn policy. RVR focuses on reasoning with verifiable outcomes. This basically, there's no preference data. There are more outcomes, whether it's a solve the problem or not solve the problem. And the typical verification is you know, right? You create some problem, or in the coding you can write unit tests and so on to verify that. So essentially, the RL is depend on this verifier in the end to say whether your solution is good or not. And even for the agentic setting, it's the same thing. So you have an evaluator in the agents to say whether how well it goes solve your problem, and then you could use that to combine with RVR. So essentially, these are all the same, basically. Even now, I think this is still relevant beyond the reasoning goes to agents. So example, of course, the first study, of course, the DeepSeek math, if you look at that paper, they are just looking at mathematical questions. Usually you have you ask something, eventually give an answer. The answer is a number, is whatever, like and some concrete number, right? These are not proof questions. It's basically just computation questions, eventually give a number. So once you have a number, then you can ask the solver, whatever the reasoning model, to produce a number. The number, you can check the number whether it's correct or not. Coding unit test, right? So basically, you write some code, you say, oh, what it should do, and then you write some test functions. Then you check various aspects of your code to make sure that they pass unit test. Once you pass unit tests, you can say, it passed the evaluation. And this one holds both for when they train the RVR, they are doing this way. Also in the coding agents, this is the same. So essentially, you want to have a test in order to make sure your code is correct. There are some structured tasks, for example, QA, and you want to have a reasoning. It's more general than math, right? Just some reasoning, logic, or whatever. And those, you need to think step by step to solve those problems. Those problems will also have answer, and those answer needs to be computed using reasoning. So why you create a new terminology? This terminology is popularized, I think, at the end of starting to be around the DeepSeek R1, but they are not. This particular terminology is proposed by another paper, not really DeepSeek R1 paper, but essentially is kind of popularized by the paper. So essentially, if you think about we already mentioned that there are applications slightly different, the requirements also different. RHF is useful, but very noisy. So you have a human preference data, right? It's kind of subjective. Reward model could be error. So-called reward hacking, we already mentioned the reward hacking. Essentially, reward hacking means your reward model has some unexpected phenomena, which especially for auto distribution data, you basically, for example, one reward people know of is the length, which we mentioned. If you increase your response length, you will get a higher reward, both for human and for LLM. The length itself certainly is not unreasonable, but this is not what people want to, because they are not increasing the content. They are more increasing just the format, or whatever you say a lot of things which are just make your answer longer, which is not desirable. So basically, you have to deal with that. Human preference data costly to construct. RVR is when you have a verifier. Basically, the simple way is just correct or incorrect, right? So then it's no need to learn a reward model. So basically, when you have a verifier, you can use that, and the GRPO is a standard algorithm now to solve that. Without learning reward model. So that's actually an attractive part, which will come to that. The open verifier exists for a subset of prompts with no solutions, right? So, so essentially you have to first solve the problem, or you know the answer to that problem. Then you do that, or at least you know a verifier. The verifier could be unit test. In that case, you don't need to know the solution. You just need to know the desired behavior, basically. Okay. So then you train that. So the train is really train the reasoning. So that's what it is. For example, this is a simple example. You say, okay, you solve this one. Of course, you salute, you get X, right? So this is the correct trace. Basically, the reasoning step is like this. So first, you subtract the 17, and then they just simple two steps, and then you get X equals 6. Then this is correct, and the incorrect one. The first step, let's say, it's still correct, right? The second step, or first step could be incorrect. The second step is correct, and then say out of 7, which basically says it's incorrect. So now at least you know that this trace, right? This reasoning trace, it generates some reasoning token as well as the final answer. But the reasoning token has to be something wrong within these reasoning tokens, because otherwise you will not have the incorrect response. Here, here you have a correct response. Actually, one thing about the shortcoming of this kind of approach is that even you get the response correct, it doesn't guarantee your reasoning is correct, right? Your reasoning could be wrong, get it right, but that is unlikely. So once you get a result correct, usually you use that as a good set of traces, which you want to use those traces to train, and you want to encourage these traces. You want to discourage these traces when you do the RL. So verifier checks, the result in this case. This is correct. In this case, this one is incorrect because the number. Typically, you also want the reasoning trace to output some fixed format, right? Like you have thinking tokens. It's similar to what we mentioned in prompt. You want to have structured output, JSON, right? Here it's not JSON. You just have some reasonable format. Like you first think, then eventually give answer. The reason is then it's easier for you, for the verifier, to extract answer. Then you're just looking at this part, is extract answer from here. So then you are okay. So this one enforce your reward. Say, oh, if this one gets you 6, it's correct. If this gets you 7, it's not correct, right? So basically, this is kind of verifier. You can also have a unit test, right? This one also is used typically in the software agents, which has similar setting, and then you have a unit test. So we'll quickly say, this is a basic background. We'll quickly say primary goal is alignment. This is the reasoning. So essentially, this one is not increasing the capability of LLM, but make it more helpful for human to interact with human. This one is really increasing the capability of LLM, in teaching them how to do reasoning. Reward source learn from human preference computed by verifier. So no learning and often subjective. This one is basically what you write is pretty strict, either yes or no. So reward model, usually you don't have to. I mean, this one, you could have a reward model, but typically you do not, right? So basically, domain is a general, right? This is more about you are solving problems. Main risk, of course, this is reward hacking, right? Misspecification, auto distribution, and so on. Here is verifier is not complete. For example, your unit test doesn't cover all the scenarios. Some scenarios not covered. Or for example, you only check the final answer. It doesn't check intermediate steps. So therefore, there are some loopholes. But even with these loopholes, you just believe in your outcome. You say, and that actually trains a very strong model. It doesn't guarantee it's never make mistakes, but it will already learns the right thing for you to perform tasks. Here is the KL regularizer, which we talked about the last time. Last 2 lectures, we both talked about this KL regularization. So the optimization still KL regularized, right? So essentially, you have prompts. This is LLM generated responses, including thinking tokens here, right? And once you give a thinking token, remember we have a format. You look at the last of your token answer token, and then you can compute this format, and then you basically evaluate that using KL regularization. So basically, this is the same objective as RHF. And the reward we mentioned, we have a verifier. This is just say the outcome is 0, 1. Sometimes you get some format say, okay, whether it contains thinking, right? You probably just say you contain thinking, right? Need to contain thinking token of that, need to contain out answer. But the model may not always follow your instruction, right? All the LLM are stochastic, so they always have possibility of not following. And if it doesn't follow, then what you need to do is you add a reward, just encourage that to follow your instruction, to output your response with a format, right? So we do have a code actually provided you can take a look at, and this is a teaching code. The code is a demo code, and then you can see how it actually works. A is a reasoning trace and the final answer, right? So verifier, correct or not, and the format, just make sure you have these. You can give some reward like that. Then once you have this reward, it will encourage your format, and especially it will encourage your verifier correctness. Okay, so this is objective. This is similar, except the source of your reward model is coming from verifier. Yeah. So yeah, our format is just to give an example. Yeah. So this is something. Okay. So RL terminology we will quickly mention just because a lot of RL using the algorithm are written in RL terminology. So we'll briefly mention in the RL what these are, right? So basically you have we said a little bit the last time as well. So when we look at the so-called trajectory, I mean state usually is prompt. Action is or response. It's basically it's a response of the LLM, both as to be contains thinking token and your final answer. So basically, yeah, from the thinking token and the final answer of your response, you can actually compute the verifier. Verifier can use this response to compute whether your final answer is correct or not. In the programming, of course, this thinking token generate code, right? And verifiers execute the code and you need to test to see whether it is. Yeah. So policy is LLM is generating response given your prompt with a model parameter theta. So this pi is basically an LLM that continues to generate response. Trajectory, typically, trajectory, you have a prompt, you have a reasoning, you have a final answer. Yeah, here I just mentioned reasoning. Essentially, I think reasoning and the final answer both A. Yeah, both A. Yeah, maybe I should remove this edge and the final answer. Entropy regularized reward is this, right? So basically, you are optimizing your general trajectory. Then you compute this number. The number is as large as possible. You want your trajectory to generate generate A such that this number is large. So basically, this is this is what it is. Okay, so yeah, so that's about especially trajectory and so on. Training is optimize the policy parameter. So remember, we do not have to train a reward for RLVR. So we do not train a reward. We just need to train the policy, the LLM, which has a model parameter theta, such that this one increase, right? So basically, this guy, the regularized reward increase. Yeah. One thing I want to mention is in RLHF, usually adding this is pretty important because reward is learned. In RLVR, adding this regularizer is not as important. Usually they put it optional, but it's not as critical as for the RHF. So So in many times, they just set this one to be 0. So in many reasoning, in some other applications, it doesn't. So it depends on your situation. So this one is lesser important. Here is a RL training pipeline, which we mentioned the last time. This so-called on policy. If you recall, we talked about policy learning algorithm like Raft, like iterative DPO. Essentially, you come out with a policy, you generate a trajectory, then you use a reward model to rate this trajectory, right? And then you update policy. So basically, yeah. So this one is so-called on policy in the sense you generate, you are doing that. From a reinforced learning perspective, system perspective, you want to generate data, you want to update your policy. This part is once you're given whatever filtered data, like either DPO, if you think about it internally, or it's SFT in the raft setting. This one is like supervised learning, fixed data, update policy, right? This one generated it. So policy comes to the different ways. Sometimes you have to update, this one is slow. I can use a separate policy to generate my trajectory, right? And then I will update the policy. So I can separate these two. So if you separate this code, sometimes it's called off policy, policy is behavior, and then you run this. Basically, you first collect the trajectory, right? You have you gather of this one, putting that together, and then you consume this data generated by certain policy. This policy may not be pi theta. Usually, it's probably theta old. It's a little bit the delay, earlier version of your theta. You do not update that one. You just keep generating policy, and at some point you update. So this one you make it a little bit async in the sense that you generate the policy. When you update the policy, this can be different. This one is more common actually in the practice. And this policy depends on what you call that. Sometimes, a lot of times, called behavior policy, where you generate the data, right? There's one policy generated data, one policy consume the data doing supervised learning. So update the policy. So basically, you always update, and you from time to time you sync this update policy to this behavioral policy, and this is more typical. And the reason we want to talk about this one is for all the policy algorithm, you want that to be you want that to be on policy, like your current policy. But here it's while you generate data, it's actually off policy. What you do, you want to do a correction. So this is so-called on policy correction or off policy correction. Basically, you make that looks like on policy. We will talk about that, right? Generated by the current policy, or policy generated by older policy. Right? Older policy is not as good as current policy. If you think a little bit intuitive, you keep improving your policy, right? If you generate by certain other policies, it may not as good as your current policy. You want to use also best policy in some sense to compute your update. Then what do you do, right? Yeah, and so what you do is we'll keep that in mind, but we will starting to do something which is well known in policy gradient algorithms. In the sense of rewriting this, because it will keeps coming up even when we look at the GRPO is the key main algorithm. We talk a little bit about other policy gradient algorithm, but mostly we will focus on GRPO, and it actually will have this form, so-called advantage, right, function. What does it mean? It basically means the following. So you have it's basically a function of the form. So your reward, right? Usually, if you think about what reward do, reward is try to say which answer is best for your prompt, right? If I have some reward, doesn't depend on answer. Let's assume there is a reward, it doesn't depend on answer. All the answer equally good, then it's ineffective. It basically doesn't affect your policy, right? Your policy cannot be changed because it doesn't tell whatever the answer you give are good or not. So therefore, you subtract something which doesn't depend on answer, only depend on your prompt. if for any such function you minus from the reward, it doesn't affect your ranking. You think about the answer ranking is what you want to learn, the better answer, right? Better way to respond to your prompt, but it doesn't do that. If it doesn't do that, then what happens is that it's basically get the same reward. So essentially, the objective function of this guy is equivalent to objective function this guy, as long as you add something to your reward, which doesn't depend on your prompt, or your response. Only depend on prompt. This we actually see when we derive GRPO. There is a normalization factor which we ignore from the reward, which is basically the same. But this one is generally used in a lot of policy to specifically construct the V so that this one becomes small. For example, Vx usually is the mean of this reward, such that you can subtract so that this number is the key part is why you want to do that is it doesn't change your objective function, doesn't change your solution in the sense. Optimizing this one and this one is equivalent, right? It doesn't change your solution, but this one can be smaller than this one so that you have a smaller variance when you do the policy gradient. The key of that is reducing variance. So this is called advantage. We will talk about that because it keeps coming up. So we have to have introduction about that. But for the sake purpose of essentially, you just say what do you want to choose? Advantage typically choose is this expected value of so-called value function. So your reward minus your value function, or any prompt which is a mean reward. You can think about it as a expected reward, right? And then it becomes advantage. Okay, so we will work with advantage because that's usually what all the policy gradient works on, and this one is roughly this one is basically has a smaller variance than R. So hopefully, so that's the main reason to use that. Okay, so let's remember this terminology. You have R, you have advantage, right? Advantage is you have a reward. Then what do you do, right? So essentially, we can optimize this function. First, our goal is to optimize this guy, right? But the data is generated. This one requires data A is generated by the current policy. What if the data is not generated by by a behavior policy, right? If your data is generated by behavior policy, what you can do is this means the data is generated by behavior policy. Then you just take the ratio. The ratio is your current policy divided by behavior policy, and these are the same, basically. You can rewrite it identical. If you are generated from one policy, you can generate from another policy, take the ratio. This is importance of weighting. Is well known in probability and highly used in machine learning in various different places. In many different places, this formula is used, especially in RL. RL because there is a way to generate the data, and the data may not be the current policy. Then you can rewrite your objective as generating using a behavior policy, which is slightly different than the current policy, and then you're doing that. This becomes from this point you look at off policy, right? When you generate the data, but this correction make it behave like on policy. So basically, this is where you see this ratio, which in when we later on talk about in quite some algorithms, they all have this ratio. Okay. So you need to have this ratio to offset your objective versus your data generation using a different policy than your current policy. The RL require current policy, right? So basically, this is okay. So the main point is you can use of other policy to generate your data. Then you do a correction, importance weighting, such that this weighting is correcting this all policy to make it behave like on policy. Therefore, you essentially can just optimize this weighted objective. This is advantage. This is importance weighting. So these are two key concepts before we talk about the actual algorithm. So let's look at the actual algorithm. Policy gradient. Policy gradient is basically trying to solve this. This is off policy, right? And then this is on policy correction. And then this is advantage. And this is minus your KL. So, and you can show. This is known for, well, it's not too difficult to show. But nevertheless, what we want to say is following is basically you have this. Basically, you can show that you have this is your KL regularized reward and the gradient of your this guy. And this one is so-called policy gradient. Eventually, you can draw this and then use this policy gradient and do that. So off policy policy gradient is basically sample prompt from some behavior policy, then update policy using this guy, theta, and then you sync this guy. You keep, at some point you sync this theta to mu. Okay, you sync to your behavior policy. So but then you're just using this formula. This formula is called policy gradient. This is this is basically policy gradient. We will try to do a little bit faster than that. And there are a lot of RL books about how this is derived, but we just take it for the formula to say this is a formula and this is updated rule. Okay. One thing is the policy gradient. The advantage, of course, is pretty simple, right? Data generation to be decoupled from policy learning. We mentioned that this is useful. And multiple PG steps can be performed before updating the generation policy, right? So you essentially you keep updating the PG, and then you generate the policy, and using this policy correction. Trajectory using the old policy can be reused. This is another thing, depends on your algorithm. Drawbacks, theta can drift away from mu. Once pi theta drift away, the ratio of rho can be very large. Very large means bad, right? It's a high variance. You don't want the rho to be larger, but it's a ratio. Ratio, if you think about the ratio of the two policy, they generate, especially when they generate a sequence of responses, can be dramatically different. So this is one problem. This causes high variance and unstable optimization. And there are ways to do that. The two things I will talk about, we will quickly mention TRPO. Just to have a high level, so what it does, right? And then we will talk about PPO, because PPO is the predecessor of GRPO. GRPO is based on PPO, but do some modification. So we should talk about the PPO. PPO also we talked about in RHF. It can be used for RHF as well. Except there are other methods as well. PPO, ratio clipping, and approximate solution of TRPO. Trust region policy optimization, TRPO. So TRPO maximize using this. This is objective. This one I'm not copying, but you remember this formula, which we say is advantage minus your KL, optimize your policy. But here it's just instead of solving this one, just get a constraint. So this particular constraint to say I use pi old to generate my policy, right? To generate as a behavior as my behavior policy to generate a trajectory, and then my pi theta, which can drift away from this behavior policy, but I want to control that such that it's not a large deviation. So this is one methods which pretty well known. And essentially, yeah, this is basically TRPO. TRPO, you are generating and subject to constraints, right? This method called TRPO, but the main problem of this one we just quickly know as an intermediate algorithm. We are not going to details, but the main trouble is it's better stability, right? Because you keep a policy close. It's a second order optimization because KL constraints are hard to handle. So therefore, the optimization is more difficult, and therefore this is not used a lot in practice. Although people could revisit it sometime from time to time, but typically this one is because of this problem is harder. Conceptually, it's good in some sense, right? So conceptually, it's good, but in practice, it's not as good. So basically, this is more or less the conclusion. Because of this, it's hard. It can be expensive to solve. And then there's the development. Both, I think, the key is both by John Schumann. John Schumann certainly was. He left OpenAI, of course, but the earlier years of OpenAI, including RHF or whatever, is the main person who work on those for the RL of OpenAI. So, and he has these two papers about RL algorithms widely used, especially PPO is one of the standard reinforced learning algorithm. So what it does the following. So it makes it simplify. And it's more directly related to this issue about rho being too large. So PPO has this criterion. Basically, it's a minimum of these two things. It's more conservative. When you maximize something, you put a lower bound. You are trying to optimize a conservative bound. This is the original RL objective, right? This one, remember we mentioned. This one we will ignore the ignore this KL for now. This one just looking at this advantage, right? Advantage. This is a ratio, right? Of policy. When you do this ratio, make it on policy, right? So the R object. This one say, oh, what if this one is too large? R, right? R is, for example, 10, right? That is not good, right? So essentially, this one says, when we do that, we want to clip this R objective to make it closer to 1. So it's just a safeguard. But because you are taking mean of this one, you are conservative, it's fine. Because your objective versus your whatever more conservative, it is okay. So here it's in practice, sometimes people say, okay, epsilon equals 0.2 or whatever, right? So, but typically, it's a small number. It's a so this one is essentially this guy is close to 1. So it's more directly addressing the issue about the compensation ratio becomes too large. It also mentioned too small, but mostly more critical is too large, right? So basically, yeah, you just make a conservative estimate, and this is much easier than say TRPO, and this works pretty well. This so-called conservative optimization. Essentially, it's mostly dealing with this correction term, right? Trying to make it either the on-policy correction or a little bit less correction. So yeah. So basically, this is an objective function. The first order, because you just take gradient. Remember, when we take a gradient of this guy, becomes a policy gradient. Here we just take gradient of this, take gradient of this guy. So just take gradient of two things, but still, we just truncate that. So you actually just truncate that to say which one wins, right? Which one is smaller? If this one is smaller, you pick this one. If this one is smaller, you pick this guy. So basically, clipping discourage overly large policy updates. So make it easier. So for LLM, actually, I just quickly mentioned this one. We will go to GRPO. So LLM, what happens is the following. So PPO for LLM, we at a high level, again, using this objective. PPO is just the key idea, again, is you need to understand that there's an importance weighting. It's a clipping importance weighting to prevent it to be too large, right? So that's the key idea. And this clipping is at token level instead of the full sequence level. Sequence is XA. A is many, many tokens, right? It's answer. But here, the TRPO or PPO is applied only at the token level, which make it more stable. So this is basically how PPO is applied for the implementations. In practice, advantage estimated using this, we don't want to talk about that, but essentially there's some technical detail, they can estimate its advantage. By using so-called value function, you have a learn value function, and then you are doing, we'll skip the details, but you can look at that. And also there's an implementation, Hugging Face TRL, which is open source, which does have a PPO, and but we will quickly mention. The key part of PPO is the following. So I would just want to say that first you have that ratio, but the ratio is compared at token level. You sum over all tokens, not just at the whole sequence level. So that's number one thing for the LLM. Number two things, you want to estimate your advantage. There is a way of estimate using the final reward as well as a learned so-called value function. Value function is basically minus this V. If you remember in the advantage, you have R minus V, right? R is known, but V is not known. So V, you try to estimate to make a smaller variance, right? The RVR, right? So we have a verifiable reward directly. No learned value model is required. Instead of learning this, I think PPO, GRPO using a way of avoid learning. The key why it becomes popular is because it doesn't learn this. Okay, this is one of the key. There's actually something else. It's slightly different, which we probably won't talk about, which will be more complicated. But basically, instead of using the generate group, which we'll talk about soon, advantage without a value function. So sample group of responses, right? So for each prompt, right, you are thinking about forming a V such that the average of your responses reward, taking average of that. And essentially, you take a group of responses which is like this average, right? You take a group of responses. Basically, let's say I generated 32 responses for one prompt. And the average of these 32 will be your V function. So that's basically where it comes. Instead of using a learned V, we use just generate multiple response. And this one turns out to be effective for this kind of RVR. For each prompt, you generate multiple response. Some solve this problem, some doesn't solve this problem, depending on your reward. But you average that, which will essentially, you can think about it of a success rate. That will be your V, okay? So you minus that. Score each response with a verifier reward, and normalize within the group to get your identity. Yeah. Apply PPO style clipping with half days weighted at the token level. So and then you just shift the PPO, basically apply exactly the same as PPO, except where A hat the advantage is computed, which are using this group-wise computation of your response. So that's the key part. So here is basically PPO versus GRPO. Okay. PPO, this is coming from the DeepSeek math paper. So they propose the GRPO algorithm. PPO itself, it's basically just you have these are different notation, right? So this is their prompt, right? And the O is what are their response and so on. But essentially, you have to learn. Here you train the model of A, right? Here, basically, basic value model needs to be trained. So this is where it says value model needs to be a policy model needs to be trained. Value model here is only train the policy. You update the policy, but it doesn't need to train a value model. So that makes a lot of easier, much easier to implement. This is why it has been heavily used for RLVR. And the key is it requires you generate multiple response for each prompt. And this is easy for LLM. For some RL task may not be easy, but for LLM reasoning, this is easy. So it's explore this structure. You are allowed to generate multiple prompts, and then instead of estimating value, you are using the group computation to compute this value. So that's the difference, high level, and this one probably you roughly know a bit. And the formula is here. The formula given. The formula is the following. So GRPO training, right? So you have a sampled response, verifier rewards. This is a group advantage, normalized advantage. Basically, this means like a V, right? R minus V is what your advantage is. It actually have a term of divided by standard deviation of R. R is basically you're generating the rewards, right? So again, the value function, as we defined, is the average over all possible responses, which will be your value function. In this case, you just estimate by empirical mean. So that's one of the simplified way to estimate, and it's effective. And then your R, each one is divided by. So R minus mean, of course, means 0, so they have a smaller variance, right? There's a division by standard deviation of R. I will not talk about that here, but this one does have an effect. This one actually somewhat matters. It does have an effect in terms of RL, but we will not discuss it here. We assume this one just for the normalization so that you are intuitively it's pretty easier, right? So you are thinking about R, normalize that so that this range becomes, it's like batch normalization, like whatever we have talked about earlier. It's the range becomes more manageable. But if you look at the objective, it actually changes our objective. So but we will not talk about that. We assume this one is just another way to do the value function. So here is your GRPO objective. This one is without KL regularization, without KL, right? So then you have this one is a PPO. So this particular formula is identical to PPO, except that the only difference is A hat. A hat is a different estimate. This one is token-wise estimation. A hat in the PPO require estimation of learn a value function. A hat of your GRPO is just this, which is much simpler. Okay, so basically, yeah, basically this is basically GRPO's algorithm. Maybe I will say this average over groups, this average over prompts, and this average generating the responses. And this one average over the groups. You have groups of responses. This average over tokens. Each response has so many tokens, and then you take average over tokens. So basically, this is basically the overall objective. Each token get a PPO style weighting, while a hat comes from a final basically verifier reward. You can add KL regularization. Again, this is a little bit technical, so we will skip. As I mentioned, in many implementations, you can set beta equals 0. but they do a trick. This one basically they say this one is equivalent to KL, which you can show. Or this one, when you integrate out this, doesn't really matter. But basically, yeah. But essentially, this one is always positive. So they use always positive for token-wise positive. They try to manage that. We will not look at the two details, but we just give this formula just so that you kind of know. So yeah, so basically, this is what it looks like, right? So yeah, we just give a little higher level. If you look at the details, the implementation is basically the implementation of GPO is pretty not too difficult. It's just like this, and you can look at the code. Code does have an explicit again teaching style implementation. It will show you how this is computed and how this loss is computed, and then you can do you can do some update, just policy update. So basically, you just go through the prompts, solve the problems, find the reward, and then you compute the advantage, then update your prompt as using this objective, and then go on. And you could also add a KL regularization. So let's look at how the result looks like. This is DeepSeek math, right? This is where they are they propose this algorithm and use that to train their model. This is an earlier model. It's not a reasoning model yet. It's a more about math model. Basically, it's a I just quickly get one of their result. They have a 7 billion model, starting from instruction tuning model, right? And then they do RL. RL is just instead of alignment, they are doing that for the reasoning, for the math solving, right? Using TRPO. So, and then what they do is this one probably is earlier than quite a bit earlier than the maybe I don't know, it's a half year or a year around earlier than this R1 paper. But essentially, they first look at the math. This guy had pretty big improvement RL when you're using the GRPO, they claims, right? Math. This is a different math data set. This one is grade school, and those are more high school problems. And then they get reasonable results. This one is a little bit of math in Chinese. They get some other results, and this is also Chinese math, and they got some results. This is English, this is Chinese, and then this. Basically, GRPO improve both English Chinese match bumpers without training a separate value model. So that's key. So basically, they demonstrate this model is effective. So all they say is the following. Yeah, effective. Any questions so far? We go a little bit faster than algorithms, so you do not have to know the absolute details, but the high level. So you want to understand what's happening, in particular this weighting, why they want to clip that, just make it more stable. And in the GRPO, you are not needed to learn a value function, right, and so on. So this is something, and the PPO, you do need to learn actual value function, at least in the original. So TRPO is a variation of PPO, but it's a separate algorithm, and it's certainly widely used in this setting. They use the algorithm to have a very good success, made more popular or more public when they applied this to their reasoning model, right? So they start to train a reasoning model and beyond the math, and then they are doing. So we will quickly talk about the benefit, right? Benefit already mentioned. That's why they are applied. This is the standard open source algorithm for the LLM reasoning and for these kind of methods. Origin post format, but you can use that for coding, for other things. GRPO is a key algorithm for training large-scale reasoning LLM. There are many papers with a minor modification of GRPO, right? You look at nowadays just huge number of papers, but the algorithm itself is pretty well established. No need to learn value function. This is the key. This makes it much simpler. And the way of doing that is by just generating multiple responses, taking empirical mean to evaluate your value function. Reduces the memory and the tuning burden. So that's good. Group relative advantage, easy to compute. Also stabilize. The way of a group using, they also divide by standard deviation, which we didn't talk too much about, but we mentioned that actually has a role there. It's not in the traditional RL, actually. When you divide by standard deviation, you have to modify a little bit to show that. Work well with a verifier, allow sparse reward at a single sample level. Basically, sparse reward means if you have a little bit difficult question, right? So let's say you draw 32 samples, maybe one sample solve that, the other 31 doesn't solve that, so it's a sparse reward. You just get a reward signal from 1 out of 32, right? So yeah, so basically, but it's allowed that, but basically, yeah, basically that's it. We will next discuss this DeepSeek R1, which is again, it's interesting to see how the reasoning model is trained. Nowadays, a lot of more refinements, but this strategy is at least in the open source, in the general domain, it's still regarded as probably one of the most important paper, right, for the reasoning model, for how do you train a reasoning model. Okay. Basically, R1 is the first strong open source reasoning model with a multi-stage training strategy. We'll look at this recipe and what you learn from that recipe. So that's basically, I think, the last part of that. Previously, up to now, we talk about algorithms, about what our VR is. That is a kind of algorithm solutions and related, mostly hopefully at a high level, but then we will talk about this R1. So what's new, right? So they have a multi-stage. This is a key new, right? So first we will look at the R0, right? So R10 is starting from base model. You can either do instruction tuning or whatever. Doesn't matter as long as it doesn't have RL in there, right? They start with a pure RL to generate. The TRL, of course, the DeepSeek is a GRPO, but of course, not everybody else is using GRPO in the open source, and plus rule-based rewards. Without SFT stage, they try to understand whether you can get your reinforced learning to get the reasoning ability, to show reasoning ability. So reward design, as I mentioned, it's just like this, accuracy and the format. This is basically what we talked about. So this is what their reward, and algorithm GRPO, right? So the effective, basically what they observe the following. So it's a very interesting, strong emergent reasoning behavior. Basically, reasoning chain of thoughts ability will get trained. They will be able to do much better. But raw performance has some other issues. It's not aligned, right? Or it's not even has SFT, although some SFT data probably in the base model, so you do have some reasoning, but essentially a lot of other issues. Language mixing means sometimes you will have your, for solving math, part of the math saying in English, another part in Chinese. So basically, then essentially, you are mixing language, which is undesirable. You shouldn't do that, right? So for a well-trained model, but this is a example. So they have various issues. Reasoning gets better, but some other probabilities, instruction following, or some other desired alignments may not as desirable. So DeepSeek R1, it's starting with R1 0, right? At some staged alignment. Basically, this is when they observe what you can do with the reasoning training, right? RL training about some just the fundamental model, what happens, right? It's good in reasoning, but not necessarily for other SFT or even for chat applications, not necessarily, right? Reasoning strength while improve usability. So they are happy with reasoning strengths about this R1, the way they can generate reasoning thoughts. But they want to see other aspects to that. So then they have a multiple stage. Okay, so this is and here is what actually the paper says about what exactly they are doing. What exactly? So first they have base model. Right, base model, they use RL training with reasoning prompts and so on, right? This becomes R10. And we mentioned that it has good reasoning ability. They are happy with that, but they are not as happy with the other abilities, right? And you are, then essentially what you do is you can use this guy to have reasoning prompts and as well as some because they can solve problems better using this model, so they can use this model to generating some data. Right. So basically, long COT data means you have some reasoning data inside your response. So they start bootstrap from this one has reasoning ability. Then they bootstrap from this one to generate some more data using this as a base model, and then generate a response because they can generate good reasoning. So they can solve some problem nicely with so-called long COT. Long COT basically just adding reasoning into your solution, right? You do reasoning, then give an answer. So basically, but because you can generate this data, now this get back to the SFT. So okay. So so here, if you SFT, then you have V3, right? V3 is the base model. Then you have using this reasoning SFT data. Presumably, when you have a reasoning SFT, you get this guy. This guy has a better starting point of RL than this guy, right? So and then this is why you do this. So then you have RL. So you essentially, the other way to think about it, they can have a kind of all policy RL in some sense. This one generated some good data to bootstrap your originally non-reasoning model, bootstrap that to be, and then you are iterating, you're getting more, and this one actually happens quite a bit in the modern days. They can iterate many times. You have RL model, you generate more data, then feed into instruction tuning data, and then you use that to train, and then you get better results. Basically, you are providing solutions to some difficult problems by using some well-trained RL model. And then reasoning prompts and the rule-based reward. This one is basically more like this one. But this time, because they observe this guy has some issues. For example, language consistency, right? They will generate reasoning in different languages. Now this one's added in. So basically, this one becomes, this one is RL model, right? This one is instruction tuned model, but has some reasoning ability because they see the SFT reasoning. But this guy is really RL trained reasoning model. And also they have, in some sense, it's more consistent than this guy, right? So now let's say DeepSeek, you are going here. The next time it's a final stage. Right, final stage, you're starting with a real SFT with both reasoning SFT from there. Here, of course, the nice thing is at least it's language consistent, right? It doesn't have this problem with language mixing, so the reasoning will be nicer. And then you also have non-reasoning model, SFT. So it's instruction tuning with both COT and non-COT data. So here. And then you get more RL you starting to retrain that. Basically, just iterative. Non-reasoning data, you could have AI feedbacks, then you can use this guy, right? So basically, yeah. So this combines a lot of things we know, right? Instruction tuning, you need to know. They didn't talk too much about alignment except here, right? So alignment, this one, again, is a reasoning. They are reasoning diverse prompt with reasoning prompts and alignment prompts, preference reward, right? Preference mean alignment. So they merge instruction tuning, right? Probably AI feedback, AI like bootstrap of your instruction tuning, all the things putting together, what we talked about. Essentially, also with our VR, with our HF, this is our HF, right? This is our VR, right? So basically, yeah. So basically, they merge this RVR and RHF in the final stage, then they get a DeepSeek R1. So basically, this is a pipeline. This pipeline essentially, if you think about the reason is you want to start quickly. If you're starting with nowhere, no reasoning model, you want to start quickly, have a reasoning model so that they can generate a long COT data, right? So they post here and they fix some issues. Then what is? Oh, generate a previous trained model instead of continue train on this. Yeah, RL model, what happens is RL model is already forget some things. Usually, I think we probably mentioned a bit, instruction tuning. All the model, once you continue training, starting to forget things which exist in the either knowledge or some other things. So it's become harder and harder to train. So that's typical. Also, you can call that entropy collapse. Remember in the RHF, we talked about that. RVR also have this issue. So you do not want to continue from there to train. This is one, okay? Yeah. So yeah, but basically, generally this is a paradigm, and this works well. Multi-stage training is also exist even in the current all the other works using, because if you think about it, eventually this AI model, right, especially good at some certain things, like reasoning or solving some math problem, then you can generate more data. Put it more general. Then eventually general data have a little bit more specialized or bootstrap model, they can generate more data. And this kind of data sometimes, I think they call it mid-training. If you hear this kind of term, instead of post-training, because they have iterated stages, right? Then you want to say, oh, does this data helpful? But this one is currently pretty typical. Eventually, you add more data, especially AI-generated data, into your training pipeline, right? And then you actually train a better model. Hopefully, multi-stage training will get you a better model. Although we exhausted the internet data, if you think about that, right? It's not, so knowledge-wise, we probably cannot do more. But there are other data can be generated, like math data, right? They can automatically solve some problems. Getting back into that in your training data, then you can solve better problems. Or like an agent setting, even more, right? Our business process and so on. If you get those data, you have a verifier, evaluator. You can keep using evaluator filter of your data. You add those in learn training build. So essentially, you can have many more data still to come. So therefore, although one exhausts the internet data, there are more data, especially in the reasoning, in the agentic setting, generated by LLM. So we are still not hitting. That's why some people say we're not hitting a wall of scaling law. Effective different stage, we should quickly mention the form pipeline checkpoints, right? So we already mentioned these, but the code start, right? Improve readability, dev one. This is the instruction tuning paper, right? So, but reduce the pure reasoning because this you're starting with RL model, that goes to instruction tuning model. So but then to RL it covers reasoning. And recover the strength math code reasoning by the rule verifier, the reward. Basically, this is RL model, right? Dev1 to DL2. This is the instruction tuned model. This is R1. And then you solve this language mixing issue. The mixed reasoning, non-reasoning, improve instruction follow and general ability, because they start with reasoning, pure reasoning, no instruction tuning, and then now you see that. And then you combine the reasoning and the preference style. This is alignment data. Finally, you can do chats, and you also can do reasoning in chats, and alignment, general quality, keep reading. So reasoning, RVR and RHF are complementary. They do not replace each other if you look at this pipeline from the Dev3 to R1. Okay, so outcome is basically you say actually they can improve reasoning a bit, because you think about you are doing a lot of instruction tuning, but also broader applicability. So they are generating, yeah. But basically that's why I think essentially just say they are complementary, and it's important, and basically yeah. I think yeah, what we can say is there are still rooms to improve. I think as I mentioned, because reasoning data can be generated not necessarily for free, but at least automatically by the AI. Okay, I think that's all. So today, then we will have a reminder is the Wednesday will be the part 2 exam, and then we will move to the part 3 next week. Okay, thank you.